guess I'll go ahead and I start. First of all, thanks for coming. My name is Șerban Constantinescu. I work in the Linaro ART team, and today I'll be presenting a bit on our process. Hopefully it's going to be a good guide for the new members in our team, and it's going to be a good guide for anybody else that's looking at working on a similar process, on a similar type of project as we do. So first of all, who are we? We are a team of 9 engineers currently, 7 engineers from ARM and 2 engineers from Spectrum. And I would like to thank our new engineers from Spectrum for joining efforts with us and helping us develop the next release of the ART optimizing compiler. So what do we do? As Scott mentioned before, we do primarily 2 things. We do Linaro ART stable, which is the stable tree. It's basically, we focus on improving the performance of the current ART release, that being Marshmallow as we speak. And we also work on the next Android release. We work on the performance improvements going into the next Android release. So here's a short diagram of our development cycle. So we start off by selecting one of the tasks that we are planning on working on, developing it, going through internal code review, and doing testing, benchmarking, mostly the process that Scott mentioned in the slides just before. And then we finally hit the upstream code review, and hopefully our patch gets merged as soon as possible and with as little changes as possible in the upstream code base. So here's how all these systems, all these development stages map onto what we use within Linaro. So you can see that the first part of the process, up until the upstream review, it's basically all hosted in the Linaro systems. And the upstream review happens in Google's Gerrit. So we do the task selection in Jira. We develop code, mostly C++ 11, a little bit of assembly code and Java. We use our internal Gerrit, and I'll tell you about how many instances of Gerrit we have and what do we use them for. We do testing using Jenkins. We do benchmarking using Jenkins and Lava. And then finally, after we pass all the tests, all the benchmarks, we see no regressions, we push the patch upstream, and we wait for the upstream code review. So let's start with task selection. I mentioned that for this we use Jira. We live as a component within the LMG project. That's the Linaro mobile group. We have 2 components for the items of work that I just described. So one component identifies the work that goes into the next Android release, and the other component identifies the work that's going into the current Android release, those being RTIP and RStable. We use Jira labels, which are used by our team to classify the ART subsystems. So for example, we have optimizations or ART runtime and so on. And we have a naming scheme over there which helps us with the Jira labels. They're searchable, they're sticky, so they're exactly what we need for identifying these sort of items. We use the fixed version for identifying things which are in our current scope. So if you look in our Kanban view, you would see the things that we plan on starting to work in this iteration. And as a process, we use Kanban with a bit of a Scrum influence, so we call it Scrumban, because we do daily stand-up meetings. It's quite good, Kanban is quite good for fast-paced upstream projects like ours. And for those of you that do not know much about Kanban, I put together just 2 slides to present you what Kanban means in essence. So Kanban was first introduced in automotive manufacturing plant. It basically splits the work that needs to be done for a task to finish in stages. So for our process, we have a to-do stage. Those are tasks that we plan on working on that haven't yet been started. Then we move in the in-development stage. Those are tasks that we are currently working on. Then we move into the review. And here we have a split between the internal code review and the external code review. We find it useful sometimes to know how many tasks are blocked on our internal code review, and we need to take a look at, and how many tasks are blocked in the external code review. And once everything is done and the code is merged upstream, or sometimes in our internal code bases, for example, for stable, the task moves to done and it's being closed. So that's the development cycle on a horizontal axis. And on a vertical axis, you have the increasing priority. So the tasks with the highest priority will always be traveling at the top of the Kanban board. This is visible in Jira, in projects.linaro.org, and you could take a look at what we do and how we do these things. There's a caveat, and I should mention that now. Throughout my presentation, you'd have all sorts of useful links. Those ones are mostly Linaro links, but for some of them, you need to be a member of LMG to be able to access them. So here's a view of our Kanban board as of 2 days ago. I don't expect you in the back to see exactly what we're working on, but it's pretty useful because as a glance, you can figure out what people in the team are working on. So we selected the tasks. We know what we're going to work on. We have a brief description of the task. And now we start developing the patch. So once again, I'm going to mention Scott's presentation. He just presented before a couple of development stages and things that would help you with developing tasks. So we developed the patch using Google's coding style. And I should mention that the Google's coding style is not actually entirely the ART coding style. So the best thing to do is to take a look at the surrounding code when you have any doubts. We develop the code, we test the code, we run the G test, the Java test, the checker tests, all the things that Scott mentioned. Then we run our benchmarks. And that's pretty much, we're done with development. So for the ART testing, there's a link to the benchmarks that we're developing. This is a list of roughly around 50 to 60 benchmarks now. As a good practice, whenever there's a code path that's not exercised by a current benchmark, we write a new one. So for example, we did system array copy char intrinsics recently, and we wrote a benchmark that exercises that path. So always when developing a patch, take into account that your patch should be passing all the tests. Otherwise, there's no good of sending it not even to the internal code review. And it should pass all the benchmarks, as in it shouldn't cause any regressions. I should also mention that we have a Linaro IRC group. That's Linaro ART. So if you have any questions or you're looking for any sort of guidance, you always find somebody there willing to help. So we move on to the internal code review. For this, we use Gerrit. As a matter of fact, we use 2 instances of Gerrit. We use a public one for our benchmarks. So the benchmarks are publicly accessible. You can take a look at our code reviews. You can probably even download the code base. And we use the private code review for all the ART patches. So all the ART patches, either for stable or for tip, are reviewed in the private Gerrit. Before submitting patches to the internal code review, all your patches should at least build and pass some of the tests that I mentioned here. So the host test would be making sure that you haven't regressed anything on the host. That's x86-64. So basically it means that your compiler builds and your compiler doesn't hurt any of the x86 and x86-64 tests. And then it should pass the target tests. And obviously these ones should be run on the target that you're developing for. If you're developing for ARM, you probably need only a 32-bit ARM device. If you're developing for ARM64, you obviously need a 64-bit ARM device. All patches that are ready for upstream review, so that's they passed the internal code review and now they're ready to be sent to Google's Gerrit, they should have a +2 from Linaro ART leads, a +1 from Linaro ART, that's the engineering side, and a +1 from Linaro automation. And as Scott mentioned before, working with upstream means that sometimes our automation is broken. It doesn't work. But a good practice is to take a look that your patch doesn't cause any regressions when compared to the base. And you should also have reply to all the comments. Sometimes it's very difficult when you have a patch that has multiple iterations to figure out if a comment has been addressed. So it's a good practice to close the comments or to reply to the comments that are not applicable to your patch. Those groups over there, Linaro ART leads and Linaro ART, expand to the proper reviewers in both Gerrits. So you don't need to figure out who's the Linaro ART leads. Gerrit will do it for you, and that's updated, and it's always up to date. So we move on to testing. And before I tell you anything about our automation, I should tell you a bit about how it is like to work with upstream. So most of the team works in Cambridge. I work in Cambridge with a team. So this is kind of how the weather looks like in Cambridge. You can see that some days are sunny, but most of the other days are rainy and cloudy. So in some sort of way, this is an analogy to how working with upstream is. Sometimes your tree might be broken. Sometimes your tree might actually build and pass all the tests. But we're working hard together with Linaro automation team and also with Google to get our upstream code more looking like this. You can see that it's much sunnier, and nevertheless, there is no rain throughout the days. So I'm going to tell you a bit about the testing that we do, either in an automated way or on a per patch basis. So I'll start off by thanking Daniel, Vishal, and Milos for all the work and all the support for all the tests and all the things that they have helped us with. So there are multiple types of tests that we run. There are tests that we trigger automatically on a per patch basis. There are tests that we can selectively ask for, again, on a per patch basis, and I'll show you in the next slides how you can do that. And there are also tests that we run on every tree update. So on every tree update, we know if the tree is building, if the tree is passing the tests that I mentioned before, those being the host tests and target tests. And we know what are the benchmarking numbers on the base. You have there 2 links to our weather reports, those being our build monitors for TIP and stable. And you can see at all times what's the current state of all the tests that we're running. Every test has a short description in Jenkins, which should help you understand what tests do. And they store a useful amount of logs and pin manifests, which would help you reproduce and understand the issues that the current test has. So I'll describe a bit the tests individually, every test that we do, or every test that we have currently implemented. And at the end, I'll tell you a bit more about the things that we're planning to do. So on every tree update and on every patch that we submit to Gerrit, we run the ART host tests. Those are the tests for x86-64, tests that build on the host and run on the host. So these include G tests, Java tests, and checker tests. And if you don't know what these mean, you could refer to Scott's slide deck, where he describes in a bit more detail each one of these type of tests. So there are 2 triggers, as I mentioned. This patch submission, every patch that gets pushed for internal review, but there's also every tree update on which we run this. So you should run this, obviously, whenever you push a patch or whenever we update a tree, but that's not something that you should bother with because we trigger these ones automatically. Every patch that hits Gerrit, will trigger one of these jobs. I'll move on to the target tests, which are similar to the host tests, except that they run on targets. So they run on ARM and ARM64. They currently run on Nexus 9 devices. And again, this test basically does all the other things that the host tests do, but doing them on target. And again, these tests are triggered automatically whenever a patch is submitted for review. So basically, testing-wise, every patch that you push would automatically trigger 2 Jenkins jobs, one being the target test and one being the host test. You could see that there's a link there. So every job has a link, and every job has a description. So you could take a look a bit more in detail, what do they do. And if you have any questions, Linaro ART IRC channel is probably the best place to ask them. What other tests we have? We have boot image measurements. Scott has mentioned previously that boot.out is a good candidate for seeing how your patch affects the Java code base. So boot.out is the collection of all the Java classes and all the Android classes compiled into one ELF file. So we basically build dex2out on the host. That's the compiler. That's basically what takes in dex bytecode as its input and spits out a binary ELF file. And we build boot.out for all the ART targets. That's being x86, x86-64, ARM, ARM64, MIPS, MIPS64, quick and optimizing compiler. So that's quite a few variants. It builds and runs on the host, and we collect the size of the out file and the time it takes to compile the particular out file. It gets triggered on every 3 updates. So on every update that we do, an update is done every 6 hours. Every 6 hours, our tip tree moves forward, following closely the upstream AOSP tree. And on every 3 updates, we trigger one of these jobs. If you're concerned with the size and compile time of your patch, you should also trigger it manually. So if you use that command over there, repo upload, and then the destination topic, that would not only trigger the host test and the G test, the host test and the target test, would also trigger a boot image measurement test. And you have a link as for the other builds to the plots and all the other useful information we generate. We also run code coverage reports. This is for similar workload. So we build boot.out for all the targets, and we collect code coverage reports. This could be particularly useful to see paths which are not exercised. To give you an example, at the very beginning of the optimizing compiler, we were blocking certain registers from the register allocator. And we soon realized that instead of blocking particular floating point registers, we were blocking integer registers. So our floating point registers, which were used by Vixel, our assembler, were free for the compiler to use. So we could have had some nasty crashes because of this. So we generate code coverage reports, which are viewable as HTML. And we do this on every 3 update or on every requested topic. And you should run this when you're concerned about paths which are being exercised or not. We also do a boot to GUI test. We plan to expand this to multiple platforms, but currently this is limited to the ARM64 emulator. So this builds on the host and runs on the host using ARM64 QEMU. So the ART version that you will be running would be ARM64 one, but it would run on the host using an emulator. So we build the tree and we boot the tree, and we basically check that the tree has booted to GUI. It generates some plots for the compile time and the time it took us to boot to GUI. They're obviously not too relevant in the case of the emulator, because the emulator has different amount of times it could take to boot to GUI. But it's going to become more relevant as we move to real devices. It gets triggered on every tree update and on every requested topic. And you should be running this whenever you're concerned with the device not booting to GUI. So that's all fine. We run all these tests. We get the failure. So how do I debug it? We should first take a look at the test trigger. Was it a tree update, or was it my patch being pushed to Gerrit? We should take a look at the test status to start off with. And that's, for this, we use Groovy, for those that know the Jenkins plugins. You should take a look at the parts console output. So that would be telling you exactly where the failure was caused. And you should take a look at all the useful logs we store. Once you have identified the issue and you have at least a shallow understanding of what's happening, you should be rerunning the tests locally. And for that, you should use the pin manifest. So for every build, we store a pin manifest. This is basically a way of reproducing exactly the same Android code base as the one that was tested. For those of you that are not familiar with Android, Android is a collection of about 500 projects these days. So sometimes changing just one project might cause a different build failure. So this is why the pin manifest is really useful, because we store the exact hashes for every tree, so you can reproduce the exact same build. And you should run the test scripts. So these are the scripts that run the Jenkins jobs, but you should run them locally. And we're working together with Vishal and the automation team and Daniel on making these scripts easy to understand and easy to run locally. They will all have a common interface. They will all have a description. It should be pretty easy to understand what exactly is failing and how you can quickly reproduce that locally so that you can debug your test. So let's take a look at an example. All those links work, and they have marked as live forever in Jenkins. So hopefully in 6 months' time, if you go back to these slides, you should be able to click on the same links, and they'll point you to the exact same job. So this is a ART target test failure. So I said, first thing we should do, we should take a look at the status. And you can see here that the status says that test 145, unlock tracking stress, fails. For those familiar with the ART compiler, would know that this is a Java test. So without doing any investigation, I already know which test is failed. And this is mostly Vishal's effort for embedding all this information into Groovy and to making it as easy as possible to have the status of the build. So what sort of trigger was it? Was it a patch or was it a tree update? In this case, it was a tree update. And if you click on that link, you would see exactly where we store this information, where you can find out if it was a test triggered by a patch or if it was a test triggered by a tree update. Okay, we've done that. Let's take a look at the parts console output and figure out why this is failing. So for all the build, there are probably millions of lines of STD output. The parts console output basically looks for filters. It looks for things like errors, warnings, debug checks, and things like this. So it's a neat way of quickly going through a very big log. So if we take a look at the parts console output, we can see that the optimizing and the default tests failed for both ARM and ARM64. So this tells us what build logs to look at. So we know that. We only need to take a look at default and optimizing logs. And here it is. As soon as we open the logs, we look for failed, and we find out what failed. This test was expecting finished, and it got a abort message. So it failed. This was the fail. So we know that what test is failing. We know where it's failing. We know what target it's failing. In this case, it's both optimizing and the default compiler. So what next? We should grab the pin manifest, which would enable us to reproduce the build locally. And we should reproduce the failure running the scripts, the same scripts that Jenkins does. So we're currently working on that. We're hoping to finish some of them through Connect. Some of the tests already have this option of running them locally. But you should be running the same scripts as Jenkins. There's nothing that you should do manually. It's grab the pin manifest, reproduce the tree, run the same script that Jenkins does, and from then onwards you can debug the failure using some of the information that Scott presented. So we move on to benchmarking. So we do internal code review. For every internal code review, we trigger tests. And then for every internal code review, we also trigger benchmarks. So one of the good things of being a Linaro guy is that we could develop the ART testing framework, which is the collection of what we consider very useful benchmarks, which help us identify and pinpoint the issues. As Scott and I was mentioning earlier, whenever we have a code path that is not exercised, we tend to run a benchmark for it. So hopefully with time, we could spot regressions easier and also have a more useful source of information for various optimizations. So again, thanks to Vishal, Daniel, and Milos and the automation team, we have all this system put together, the benchmarking system. So for this, we use Jenkins and Lava. For every patch that gets pushed to Gerrit, we trigger a Jenkins job. And the Jenkins job would do some building, would pass on the build to Lava, and would run the benchmarks on the Nexus 5, and soon on the Nexus 5X as well. So we do this on every patch that gets pushed for review, but also on every tree update. And you have here some useful links to some of the graphs that we generate, but also to some of the ART reports that we collect for every build, where we can see a difference between the code, the base and the patch, or the base and the previous base, or on a weekly basis, seeing how we compare to the previous week. So we collect performance numbers. That's basically how fast we are to finish. We collect compile time, how long it takes to compile, how long it takes to generate a particular road file from the DEX input. And we collect size information. So how big is the binary that we generate? Here's a view of the ART reports. So the ART reports is basically a standalone website that has all the information about all the stuff that we do with regard to benchmarks. So in this case, you can see that all the jobs mentioned here are for particular Gerrit patches. So for example, the first one, the 412 build, corresponds to the change number 518, patch set 10. And those are Gerrit numbers, so the patch set and the change that was pushed. And here's an example of our ART graphs. This is still early days, but they're starting to look quite nicely and to be quite useful. So you could see this is for a benchmark that we wrote for system array copy. And you could see how the performance was measured on different days. So you could see how we compare to the previous day and what we pick up from upstream. We wrote the benchmark and we submitted the patch upstream. So when the patch gets into the tree, we expect some of those to go up, the performance to go up for some of them. So it's a useful thing to integrate your benchmark before you submit your patch, because this way we can collect numbers for the benchmark that you have just implemented. So as I mentioned, currently we only do benchmarks on the Nexus 9. That's because this is one of the most stable Nexus devices, and it obviously predates the Nexus 5 and Nexus 5Xs. Sorry, the Nexus 5Xs and the Nexus 6Ps. We're hoping that soon we'll be moving to those, so we collect more useful and performance numbers. So how does it work? For every patch that we push, we trigger a build in Jenkins. This is basically building an image for the Nexus 9. Then we start a Lava job that would basically take the images that we just built in Jenkins, flash them on a device, and start running the benchmarks. We run the benchmarks for ARM and ARM64, and we store all the results in the database, and we send reports currently by email and post it back to Gerrit, but soon we should have them available in the ART reports as well. So we do this on every 3 update and every patch submission so that we know how your patch compares to the base. And you should obviously run this on every patch that's submitted. That's done automatically. It's probably good practice, as we mentioned throughout our slide decks, to run this locally. So develop, test, benchmark, and then push the patch for the internal review. There's no point of pushing the patch and figuring out that things don't build or things cause huge regressions. So here's an example of a benchmark run. You have there all the links. They're currently not too easy to get to, but if you follow the links that I've put together here, you could easily reconstitute the links for your build. So we have the Gerrit patch that triggered the Jenkins build that builds a system image, which we store, and then the system image triggers some Lava, the Jenkins build triggers Lava, and you have all the links to the Lava jobs in the ART reports, as well as the raw results. So you can see here some of the raw results, some of the measurements for various benchmarks, in this case for 32-bit, but in the same link you have the ones for 64-bit. So there's obviously more work to do on testing and benchmarking. It's still early days, and we're working a lot with the automation guys. Also, Google is implementing some changes upstream, which hopefully will be helping us out. They're doing pre-merge testing, so that hopefully is going to be sunnier weather coming our way. So first of all, we're working on more stable tests and a more robust infrastructure for testing. We want to see as less sporadic failures as possible. We're working on the ability of running the same scripts that Jenkins runs locally, sometimes doing things slightly differently might be causing a different test failure. One of the big changes one of the big differences between running the test locally and running the tests in Jenkins is that in Jenkins we use a chroot sort of environment. So we only flash the ART version that we want to test in the data partition. So the system still runs a marshmallow or a lollipop image, and we just do our testing on ART. We want more devices, so we want to integrate the Nexus 5 X's. That's on its way, coming soon. The Nexus 6Ps and any future devices that would be of interest to us. We want to collect various performance metrics and various compilation metrics for all sorts of useful APKs, so APKs that are actually used by users of Android. We want to have automatic benchmarking profiles, so we push a patch, we figure out that something goes slower, and hopefully soon we'll have our perf framework, which we have developed on top of perf, saying to us that your hotspot is in this function, the load that previously Scott showed you in his slides. That's causing the issue, so that's where we should be focusing our efforts. So our patch has been pushed for internal code review. It triggered the tests have passed. It triggered the benchmarks. Question? Okay. It triggered the benchmarks, and now we're ready for upstreaming to Google. So You should always use 2 trees, one tree for your Linaro code review, so one tree where you develop things, you push them for the Linaro code review, and a separate tree for AOSP and pushing patches to AOSP. That's because we don't want to pollute things. We don't want to end up pushing things to AOSP that haven't been internally reviewed and haven't passed all these things, because we'll just get a -2 straight away, and it's better to get that in our internal Gerrit rather than bugging upstream. All the patches you have submitted should have a +2 in the internal code review, and that's from the Linaro ART leads. They're the only ones that could give you a +2. So for small fixes, if Upstream asks you to change a comment or remove a white space, there's no need to run through all this process. It's a good practice, though, to keep the patches in sync, as in, I update my patch, I push it to the Linaro Gerrit, and I also push it upstream. For all the other things, which are not small fixes, like major reworks, new features, you would need to go through all the process. And you should always have the Linaro ART leads as reviewers upstream, so that we could keep a track of the patches that are in review upstream, so that we could keep a track of the comments, so that we could answer to some of them when you are on holiday or working on some other thing that's higher priority. So that's pretty much it. Hopefully I have some time for questions.
Thank you. I have one basic question. So what is the benefit of doing upstreaming to AOSP through your team as a Linaro member comparing to doing upstreaming as an individual company? Thank you.
I would ask you back, what's the benefit? So I think, first of all, we have a good relation with Google. Some of the team is part of the team that has worked together with Google on the Android 64-bit port. We know the ART team fairly well. So we have, between us all, we have a good understanding of not only ART, but Android as a whole. We have a good ramp-up process. We actually do lots of presentations. We have a weekly ART class where almost every week one of us presents to the other ones. I think we're fairly open to questions, suggestions. We're willing to help. I think it's definitely a good way to contribute to ART and to get some of your engineers familiar with what we're doing here. We have almost, I would say that probably 80% of the ARM64 optimizing compiler is contributed by us. So that's a huge learning curve for us and a huge opportunity for us to influence the overall compiler design. As you probably know, Google basically accepted us doing the ARM64 backend, which is pretty important, and they consider us having a useful influence and a useful opinion on some of the things that they would like to do. Does that answer your question? Any other questions from guys that are not in my team?
Next job, the memory efficiency or the install time or performance?
So we focus on most of these things. We focus on performance, but we also focus on code size and memory efficiency. So currently that's driven mostly by us and by our product manager, which is here. But this is, I think, where some of you guys could help us out and hopefully help us figure out what we need to do in the next Android revisions. So if you guys would come to our team, not only we would be very happy to help and ramp you up, but also we would be very happy to hear from you on what's actually important for you.
For the 32-bit and 64-bit, which one is the, you think, most important part in the future for our task?
I would like to answer that, but I'm afraid I don't know the answer. It's probably what developers are gonna work on, what developers are gonna have as native applications. I think there's definitive advantage by going 64-bit in some regards. So, for example, if you do long operations, float operations, and so on, there's a definite performance advantage. People would say, yes, but 64-bit has bigger pointers. And I would say, no, because in ART we use compressed references. We don't take the impact on having 64-bit pointers. Our heap is currently only 4 gigs. So our references to objects are still 32-bit. So from the ART point of view, and that's a managed runtime, that's not C code, that's not C++, that's Java code. There's a definite advantage to 64-bit. Where would it go? Where developers are gonna invest more. So if all your applications are gonna be 64-bit one day, that's probably the best way to go. If all your applications will be still 32-bit, then we probably need to work hard on making the experience as best as possible on that.
So 2 questions. One, how much more work is remaining on ART optimization now that we have been doing this for a long time? And what areas do you think are going to be more challenging? And the second question was, like, in bootcamp somewhere I said, like, somewhere I heard that they were planning to go with Dalvik again, like in few instances. I don't know what exactly they mean by that, whether it was like for the app compilation or something. So I thought of checking with you.
So the first question was how many optimizations are left in ART. I would reply to that by saying GCC is probably around for 25 years. They still have work to do on it. There's still new things coming along. There are either new architectures or new architecture variants. There are new CPUs. There are new fancy things that we could do. Compilation is a huge space. There are lots of things that we currently don't do. I heard recently about optimistic optimizations, where you try to do something as fast as possible, and then if at runtime your numbers don't add up, you bail out of it. That's a thing that we could do in the future. There are lots of things that we can do. We have a full list of stuff that we would like to work on. I think CMD going forward would be a big one for ART and for the virtual machine in Android. There are people who probably try to do it every now and then, but probably didn't got it right all the way. So there are lots of things that we could do. As for the other things, I'm afraid I can't comment on that. I don't believe Google has any intention to going back to Dalvik. Probably Google has an intention to go into a different compilation mode or to a mixed compilation mode.
Can you share the feature you want to develop in ART 2?
So the features that we're developing. So we're working on instruction scheduling. We have pushed the patch upstream. We're happy to hear from you guys what's probably not working or what's probably too idealistic. So we're working on instruction scheduling. We have some ideas on SIMD. We're working on all sorts of instruction optimizations. So that's instruction simplification passes. Scott gave you an example where you do shift, you do sub, and then you do a shift in unsigned shift, and that's a rotate. We could do that better with one instruction, one single ARM64 or ARM instruction. We work on intrinsics. We basically work on lots of different things, code size optimization, metadata optimization. There are various things. If you want, I could give you a breakdown of this after the meeting. Any other questions? Thanks for coming.